Isip na Hub.
Welcome to another episode of our series on limits. This time, we're going to discuss some important strategies in computing limits.
But before we continue, do not forget to like this video, hit the subscription and notification bell to stay updated of future videos.
The first one is called substitution. Although this is not applicable to all functions that we may encounter, this is really helpful, especially when we are working with polynomials like we see here. This is just a polynomial. And really, for polynomials to compute for the limit as x approaches any number, the limit is actually the same as the value of that function at that particular number, the number that we see here, if only it exists. Well, of course, that exists because we are talking about a polynomial here. So our strategy to compute for a limit is really to solve for the value of the function at that particular number, that number that x approaches to. In fact, we can prove that for any polynomial, the limit as x approaches a is just f of a. Let us write that. For polynomials, say f of x, so f of x here is a polynomial. The limit of f of x as x approaches a is just the same as f of a. This is only true for polynomials in some other functions. So that to compute for this particular limit here, what we're going to do is just to compute for f of 1. What is f of 1? What do we mean by f of 1? The value of the function if x is equal to 1. So substitution. We have 4, 1 raised to 4. We are substituting to this function minus 5, 1 cubed plus 3, 1 squared minus 1 plus 9. 4, that is just 1. 1 raised to 4 is just 1. Minus 5. 1 cubed is just 1. Minus 1 squared is just 1. So we have 3 minus 1 plus 9. This expression is simplified as positive 4. That's the answer. That's the limit. Another example, we have 1 over x plus 2. Now, if x is approaching negative 2, for instance, then we cannot really apply substitution here. That is because substituting negative 2 here would give us an undefined answer. But we are lucky because we are not computing the limit of f of x as x approaches negative 2. We are computing f of x as x approaches 2. And if we use substitution, meaning the value of the function at x equal to 2, does it exist? Let's see. 1 over substitution, we have 2 plus 2. Our answer is 1 over 4. It exists. Therefore, we can say that the limit is just 1/4. So again, these are just cases where the limit as x approaches a particular number is just the same as the value of the function of that number because they exist. Just a warning though, I am reiterating this because substitution is not always applicable. Take, for instance, this example. We have limit of square root of x minus 2 as x approaches 2. We might say that the limit is the value of that function as x approaches 2. What is the value of the function? So our function here, say f of x is square root of x minus 2. Now we want to compute the limit of that function as x approaches 2. So we may say that the value is f of 2. If this exists, that is already the limit, we might say. So we have 2 minus 2, that is 0. Square root of 0 is 0. 0 is a number, it exists. So can we write that the answer for this particular limit is 0? Is that correct? It's not, because we are neglecting something here. If we are going to draw the graph of square root of x minus 2, what do we have here? That's 2. This is actually a curve that looks like this. This means that at the left side of 2, the graph or the function does not exist. There is no part of the graph that we can see at this part. That is because the function is undefined for anything that is less than 2. Say 1. What is square root of 1 minus 2? That is square root of negative 1. And negative 1 is not a real number. Therefore, from the definition of limits that we had, that is, the limit from both sides must exist is violated. There is no limit from the left side of positive 2. So we cannot really say that the limit of square root of x minus 2 as x approaches 2 is 0. This is wrong. The answer is not 0. The correct answer is D and E. It does not exist because the left-hand limit does not exist. Unless the question is the limit of square root of x minus 2 from the right side of 2. Then that's the time we can say it's 0. Or we are evaluating the same function, x minus 2, square root of x minus 2, but x approaches a different number. Let's say 4. There is no problem with using substitution to compute for this limit. Square root of 4 minus 2 is square root of 2. We can safely say that the limit is square root of 2. Because both of the one-sided limits of square root of x minus 2 as x approaches 4 exist. We can verify it in our graph that from the left side and from the right side, that is the limit. The number that we see here, the number corresponding to 4. Another strategy that we can apply is by simplifying first our function, especially for the case of rational functions. So we have x squared minus 1 all over x minus 1. We are going to identify the limit of that function as x approaches 1. We cannot apply substitution here because upon substitution, we would have an indeterminate form. We would have 0 over 0. Substituting 1 to this expression here would give us an indeterminate form. So we cannot really apply substitution. But if we simplify it first before applying substitution, we can actually identify the correct limit. How do we simplify this function? We need to recall our knowledge on factoring first. So we would have limit as x approaches 1. How do we factor the numerator? We cannot really do anything about the denominator. That's really simple. But we can factor our numerator. That's a difference of 2 squares. How do we factor out a difference of 2 squares? This is the formula. If we have 2 perfect squares and the operation between them is subtraction, we can factor this one as just the square root of the both of them, a and b. We write them as binomials but with differing signs. So one is a plus b, the other is a minus b. So a and b here are x squared and 1. Their square roots are x and 1. So the factors are x plus 1 and x minus 1. You see here that this is just 1. So we are actually only left with the limit of x plus 1. And it becomes a polynomial. So substitution now is allowed. Our answer is simply 2. Because if you substitute 1 to x plus 1, we would have another example. We have this one, x cubed minus 27 all over x minus 3. We first simplify by using our knowledge on factoring. This is the same as the limit of that function as x approaches 3. Again, the denominator is real simple. We just have to copy that. But for x cubed minus 27, we can factor that. How do we factor a difference or a sum of two cubes? Let's have a review. If we have two cubes, either that is a sum or difference, we can factor that as first taking the cube roots of the two numbers a cube and b cube. So if you take the cube root, we have a and b. And then follow whatever the operation that you see there. If it's addition, then write addition. If it's subtraction, then write subtraction. That's our first factor. And then for our second factor, that would depend on that first factor. How is that? The first term here is just the square of the first term there. So we have a squared. Whatever that is, this one, you just square it. And then negate the sign. If this is positive, it should be negative. If it's negative here, then it should be positive. And then multiply the two terms, a and b. So we have ab. And then the last one is to square the last term. That is b squared. Let us apply this one to factor x cubed minus 27. What is the cube root of x cubed? That is x. Follow the sign. So that's minus. Cube root of 27 is 3. And then, as we discussed, the next factor depends on our first factor. So we start by squaring the first one. Square of x is x squared. Negate the sign. So that's plus. Multiply. 3 times x is just 3x. And then the square of 3 is 9. So there we have it, our factors, x minus 3 and x squared plus 3x plus 9. We can see that we can simplify this one as 1 so that we are actually only left with x squared plus 3x plus 9 as x approaches 3. This is again a polynomial, so we can apply substitution so that the limit here is just 3 squared plus 3 times 3 plus 9. We have 9 plus 9 plus 9, 3 nines, that gives us 27.